direction every second?
DC.
50% chance of being right. Why is it DC?
Because it's coming out one way.
Right, well, is this an AC or DC source? Maybe should be in the question.
It's AC.
An AC
Oh,
source.
sorry, DC.
Yeah, you're just going to keep saying this. AC, no DC. No AC, no DC. Right. Michael, I'm asking you not to do it for a reason, so please don't do it. Thank you. Right. Is this, hands up. AC? DC? Okay. Hands down. Yes, it is DC. Batteries are DC. They are direct current. Now, what does it DC mean? Not what does it stand for, because it stands for direct current. But what does that mean about what does that mean about the flow? Do you just have to hold his hand there? All right, okay. Fair enough. If you like, if you're into that, Alison.
One side's always going to be negative and the other one's always going to
Okay,
be positive.
so in a DC source, one side's always negative, one side's always positive. What can you tell me about the flow of current then in a DC circuit? Michael, what can you tell me about the flow of current in a DC circuit? If one side's always negative, one side's always positive, what can you tell me about the direction in which current flows?
Goes one way.
One way, and only one way. It doesn't go any other way. If I turn that battery round, like if you take some way batteries in it and you turn the batteries the other way, it doesn't work because the current needs to flow a certain way. So in this circuit here, the current is going to flow out the negative side and round, one way. That's the way the current's going to flow. Okay, it's going to get pushed round that way. This is a direct current, one direction. And this one here, after a certain length of time, the current in the circuit's going to drop to zero because of the charge building up the capacitor opposing the motion of the charge. So if I was to look at a graph, now we'll look at this in a bit more detail tomorrow. If you have current against time, the current's going to start off at a high value, and as the charge builds up on the capacitor, it's going to drop to zero. You're going to get a graph which looks like that over time. Because you get charge building up in the capacitor opposing the motion of the charge coming down, eventually balancing it off, and the potential difference ends up being 6 volts. If I also look against voltage and time, what is the voltage across the capacitor to start with at the very, very, very beginning?
0.
Don't shout, please. Fraser?
0.
And what is it at the very end? Carson?
6.
And as it goes like that, you find it goes up like this, and that would be 6 at the top. Okay? Now that's a graph for a DC circuit of charging a capacitor. Now the opposite of that is a discharge graph. David, you're not paying attention. So that's charging a capacitor. I'm not going to look into that until tomorrow, but that's how a capacitor charges up. Now, next we need to think of an AC source and what that's going to look like. This time we've got an alternating current supply. Now we represent that with a positive and negative, and we just put a waveform in the middle, and that shows it's an alternating current supply. What are the properties of an alternating current supply? What can you tell me about it? In fact, maybe I shouldn't actually have the positive and negative one here just to make it a bit easier to understand. What can you tell me about an alternating current supply? Now, quite a lot of people are answering the same. Dylan, you haven't answered it.
It's never at one value. It can fluctuate.
Okay, it fluctuates, it changes. Now, going by the fact I've drawn a wave in here, if I was to draw the output from the supply, it would look like a wave. It would go up and down, change direction.
Fluctuate.
Fluctuate. Okay, Ross, tell me something else. What else can you tell me about an AC supply?
The current changes every second.
The current changes what every second?
Direction.
Direction, good. Changes direction every second. So this is what the wave is shown here. Now this would always be on an axis, like that. That would be positive, that would be negative. So you'd have your positive direction and your negative direction. It would change direction every second.
Well, that depends what frequency it is.
Well, obviously, yeah, but so many times a second is frequency. So it still has that changes direction so many times a second. Okay?
Is
So-
alternating current the main supply?
Pardon?
Is alternating current the main supply?
Yes, main supply is alternating current. Now, that means it goes round one way, and then it changes and goes the other way, and goes the other way, so it's going to change direction every second. It will change so many times a second. Alright? Now, what we want to know is, how does that affect the capacitor? So let's start off and think about what happens. So the charge, let's say it goes clockwise to start with. So charge is coming round, building up in the plate, like this. Right, so it's built up in the plate and then it changes direction. Okay? So we've built up some negative on one side, some positive on the other, and then it changes direction. David, put your pen down.
Would it just be neutral?
Third time I've said your name this period. Just listen, pay attention.
Would it just not be neutral then, because you've got plus negatives on both sides?
Right, let me just, so it goes round this way first of all, it builds up current on one side. And then, so many milliseconds or whatever later after that, it changes direction and it now goes this way. So the current's now coming this way. You had positive, that quickly discharges, and you end up with negative on that side.
What?
Okay? Negative on that side. So you had a certain amount of charge across it. So right now, so if we measure potential difference across this capacitor, then that's going to start off a certain value. Okay? Then it's going to change direction, and this positive side will become negative, and it'll be the negative value of that. But what do we always seem to have happening? If this happens here, then it happens here, the discharges builds up, and then it comes down the other side, discharges builds up, goes the other side, discharges builds up, and constantly discharging and building up either side of the capacitor. Now what is different between that and the DC circuit we saw 2 minutes ago? What is happening here that just seems to not happen in the DC circuit a minute ago? Andrew? What did we see happening in the last circuit that's just not happening here? Because it's building up, discharging, going another way, building up, discharging, another way. Pardon? Current's never zero, because we've always got a flow of charge. It might be one way, then it might be the other way, but there's always still a flow of charge, so current doesn't flow to zero. In fact, if we set the frequency correct, then we can get it so that current is constant. Current will be constant, depending on what frequency we set. And what we say is that capacitors have a frequency response. They will have a different response, the current will change depending on the frequency. So, if it has quite a high, so let's draw a little graph here. This is current, this is frequency. If the frequency is high, what will the current be? If the frequency is high, so it's changing, each side's very, very fast. What will that be high? Will it be a high value of current or a low? It will be constant, you're right, but will it be a high value of current or a low value of current? Ross? Low value, why do you say low?
Because it doesn't have enough time to build up a lot of distance.
Okay, you're right, it doesn't have enough time to build up. But what does charge building up in the plate do to the current, as you've seen happening in the DC circuit? In this circuit here, as charge was allowed to build up, it lowers the overall current in the circuit. So if you don't allow charge to build up in the plates, then you're not allowing any charge to build up to oppose the current. So if we do allow charge to build up in the plates, okay, with the frequencies really low, what will the current look like? What will the current look like? Scott, can you think about this one? So if you do allow current to build up, if you allow charge to build up, the current will be low because that opposes the charges. Correct, good. Okay, so the current will be low to start with. So if it's a low frequency, then you allow charges to build up in the plates, and the overall current in the circuit will be low. If you change the frequency really fast and you don't allow charge to build up in the plates, then the current will be high. So we end up with a graph that looks like that. That says that a capacitor has a frequency response. Alright? So, capacitors have a frequency response. The higher the frequency, the less the charge is allowed to build up in the plates, the less the charges oppose the current from the battery, and therefore it stays nice and high. Right, just a thought. Let's think about a slightly different circuit. Let's take our AC supply again, and let's pass it through a resistor. Okay, let's pass it through a resistor. Now I want to know what the frequency response of this would be. What's going to happen here? If I change the frequency, what is going to happen to... Right. So these are the three graphs that we got, or suggested graphs we got. The one on the left here suggests that as you increase frequency, the current goes to zero. So the higher the frequency, the lower the current. This one here, the middle one, would say that as you increase frequency, it does nothing to the current. And the last one here is the same as a capacitor, which says that as you increase frequency, then you increase the current. Now, how does a resistor, what does a resistor and charge have to do with one another? Can charge flow through a resistor? Can charge flow, simple question, can charge flow through a resistor? Adam,
Yes.
is there anything to stop the charge flowing through the resistor, Dave? Resistance, which it takes a share of the voltage, but in terms of current, is there anything to stop? Nothing to stop it. Is there anything to store charge in a resistor? Anna? Is there a dielectric material that can store charge? No. What is a resistor? What, physically, if I was to look at a resistor, what is it? A square? No, but what is it made of? Metal. It's just a piece of metal. Different thicknesses of metal have different resistances. The resistance is, it resists the flow of charge. It doesn't stop it, doesn't store it, it just resists it. It just allows it makes it flow a wee bit slower. Okay? So, if I turn this on at a low frequency, charge will flow through it. It might flow slowly, but it will flow through it. If I then increase the frequency and change the direction in which the current's going, the current's still flowing through it, it's still flowing as quickly, but it's just changing which direction it flows through it. It does not limit the current in any way by adjusting the frequency. So the frequency response of a resistor is that one.
Yes.
It has no frequency response. The current is constant for a resistor circuit. So bear that in mind as well. It comes up a lot. How they try and confuse you, you try and trick you into doing a capacitor graph. But its resistance has no frequency response, capacitors do have a frequency response. Alright? So the two things for today was I'm trying to work out, remember what AC and DC were, and get the frequency response of a capacitor and a resistor, and have a start thinking, have a look about what happens when you charge up a capacitor. Okay? So let's take our jotters and let's write a wee summary of what we've just done here. Okay, so charge and what's done, a capacitor is made from two parallel plates with a dielectric material between them. This dielectric can store charge. The more charge stored, the greater the potential difference across it. Here's your circuit diagram, a circuit symbol and the little formula there. We're saying that Q is direct proportional to V, charge direct proportional to potential difference. Charge direct proportional to potential difference, Q is direct proportional to V, and put into a formula, Q equals V times a constant. Where Q is charge, C is capacitance, P is potential difference. This formula at the bottom is the one you get in your data book. Finally, energy stored in a capacitor. Look at this one here. We'll finish this off next day. Work has to be done to get charge into the plates. The more charge on the plates, the more energy required to put more charge there. Okay, we'll kind of finish that off tomorrow.